So we can extend our partial differentiation to derivatives in higher order. Okay, so let's think about a function f, okay, which may be a function of two variables, x and y or more. And we looked at the partial derivative df by dx. Okay, and if it's just a function of two variables, then this means differentiate with respect to x, holding y constant. Okay, if it's a function of three variables, x, y, and z, this means differentiate with respect to x, holding y and z constant. Okay, now we can take higher order derivatives of this. We can take the derivative, partial derivative, with respect to x of df by dx. Okay, and this we write as d2f by dx squared. Okay, or if you want to be lazy, just as fxx. Okay, we can also do the partial derivative with respect to y of df by dx. Okay, and we write this as d2f by dy dx. Okay, this comes first. The derivative with respect to x is first, and then y. And we can write this as f x y. Okay, partial derivative with respect to x first, and then with respect to y. Okay. Similarly, if it's a function of two variables, f x and y, then we have df by dy. Okay, and we can do d by dx of that, and that will be d2f by, this time it's dx dy. Okay, so notice the difference in the order. This is yx, this is xy, and we call this fyx. Okay, and last we'll have d by dy of df by dy. Okay, and this is d2f by dy squared. Okay, or just fyy. Okay, so it's straightforward. You just do the same thing more than one time. Okay, so these two things are called mixed partial derivatives. Mixed. And just to be clear, by this we mean df by dx holding y constant, and then we take the derivative d by dy, and here we hold x constant. Okay, so we differentiate this thing with respect to y, holding x constant. Okay, so let's think about an example. Let's think about the function f of x, y equals x squared y cubed. Okay, and we know that df by dx equals the differential of this, the derivative of this, holding y constant. So it's 2xy cubed. Okay, we know that df by dy is equal to, we differentiate this with respect to y holding x constant, so that's 3x squared y squared. Okay, so what do we have for each of our four cases? We have that d2f by dx squared is equal to, so it's the differential of df by dx with respect to x. Okay, so it's d by dx of 2x y cubed, okay, which is just 2y cubed. All right, and we need now d by dy of df by dx. Okay, so this one, d2f by dy dx, is given by d by dy of df by dx, which is 2xy cubed. Okay, so we now differentiate this with respect to y, holding x constant. And this gives us 6xy squared. Okay, now we want to find d2f by dx dy. So this is d by dx of df by dy. Okay, and df by dy is 3x squared y squared. So we differentiate this thing in the bracket with respect to x, holding y constant. And what do we get? We get 6x y squared. Okay, and then finally we want to do d by dy of df by dy. So it's d by dy of 3x squared y squared. Okay, that's what df by dy is. So again, we differentiate with respect to y and hold x constant. So this is just 6x squared y. Okay. Now, if you look carefully, you'll see that these two are equivalent. That d2f by dx dy equals d2f by dy dx. Okay, and in general this is true for any continuous function. Okay, so this partial differentiation is commutative. Okay, it doesn't matter what order you take the derivatives, you'll get the same result. Okay, so let me just restate that very important point that if we have a function f and we take a mixed derivative, dx dy, then this equals the derivative with respect to y and x. Okay, so if you take the second order derivative, partial derivative, then it doesn't matter what order you take the derivatives in x and y. Okay, so you can show this is generally true by just considering the definition of the limit of the difference in f. Okay, that's how we defined our partial derivative. Okay, so this holds generally for continuous functions. All right, what about higher order derivatives? Well, yes, we can have d 3f by dx cubed, okay, or d3f by dx squared dy, okay, or d3f by dy squared dx, or d3f by dy cubed. Okay, and if you've got a function of three variables, x, y, and z, okay, then you can have df by dx, you can have df by dy, and you can have df by dz. Okay, and you can take mixed derivatives and higher order derivatives in all x, y, and z. Okay, so this means you can have d2f by dx squared, or d2f by dx dy, or d2f by dx dz, okay, or d2f by dy dz, okay, or d2f by dy squared, or d2f by dz squared, okay, etc. You can swap x and y and x and z around. Okay, this goes on, and you can have d3f by, you can have dx cubed, you can have d3f by dy cubed, you can have d3f by dz cubed, and then you can have all the mixed terms, d3f by dx squared dy, etc. Keep going. Okay. All right, so hopefully that is clear. So you already know how to do one partial derivative, which means you already knew this, okay? You just do the same thing again, okay? So a higher order partial derivative is just take the first partial derivative, as you know how to do already, get the answer, and then take a partial derivative of that. All right. And this is important to be able to remember. Okay. Okay, so let's finish with an example. we've got a function of three variables, x, y, and z, and the function is xz plus z squared sine xy. Okay, and we want to take these, we want to find these mixed partial derivatives. Okay, we want d2f by dx squared, d2f by dx dy, d2f by dy dx, and d2f by dx dz. Okay, so what do we need? Okay, so if we start with the first one, this is d by dx of df by dx. And what is df by dx? It's the derivative of this thing with respect to x, holding y and z constant. So the derivative of xz with respect to x is just z. Okay, so we're holding y and z constant. Plus z squared, okay, because z is a constant. We differentiate sine x, y, okay, with respect to x holding y constant. So this is just cosine x, y. We then need to differentiate the inside the bracket, so we get it times y. Okay, and now we're going to differentiate this thing with respect to x holding z and y constant. Okay, so the first term goes dz by dx is 0. Okay, so it's d by dx of this thing, so it's y z squared, so y times z squared, and then it's d by dx of cosine xy, okay, which is minus sine xy times another y, so you get a y squared. Okay, so it's minus y squared z squared sine x y. Okay, so that's the first one. Then we want to think of the second, d2f by dx dy and d2f by dy dx. Okay, so let's do this one first because we've already got df by dx, it's this thing. So d2f by dy dx is d by dy of df by dx. Okay, and df by dx is this thing, it's z plus z squared cosine xy times y, so let's put it in like that. So we want to differentiate this thing with respect to y, holding x and z constant now. So again, dz by dy goes, okay, and we've got z squared. So we're differentiating y cosine xy with respect to y. So we've got two terms. We'll have, if we differentiate the y first, then we'll have cosine xy, okay, and then we have plus y times the differential of cosine xy, okay, which is minus sine xy times yes, in this case we're holding x constant, we're differentiating with respect to y, so then we get an x from inside of the bracket here. Okay, so that's that result. Let's think about this one. This is d by dx of df by dy. Okay, and what's df by dy? It's equal to z squared cosine xy times x. So it's x z squared cosine xy. Okay, and let's differentiate this with respect to x, holding y and z constant. So we'll have a z squared cosine xy. All right, we differentiate x, keep this the same, plus we now differentiate the other term. So we've got x z squared, and now the differential of cosine, which is sine xy, and we have a y out the front. Okay, and we get a minus here. Okay, and you'll see that we've got z cosine xy, z squared cosine xy, okay, a minus, and we've got x, y times z squared. Okay, so these two things are the same, as expected. Okay, because we know that d2f by dx dy should equal d2f by dy dx if these two things are continuous. Okay, and these are continuous functions. Fine, good. All right, and then finally we want the second derivative d2f by dx dz. Okay, so in this case we want to do d by dx of df by dz. Okay, and in this case df by dz is the derivative of this holding x and y constant. So df by dz is x plus 2z sine x, y. Okay, so we hold x and y constant and just differentiate this with respect to z. Okay, now we need to differentiate this with respect to x holding y and z constant. Okay, so we get 1 plus 2z, okay, it's just a constant, and then the differential of sine xy is cosine xy times y. Okay, so it's 1 plus 2yz cosine xy. All right. Okay, so I just wanted to show you those just so that you have in your head clearly what you hold constant when you're taking the derivative. Okay, so when it's d by dx, if you've got a function of three variables, x, y, and z, then d by dx means the same as holding y and z constant. Okay, so this is acting on something, in this case f. Okay, and d by dy, or df by dy, let's just put the f in. Okay, means differentiate with respect to f, differentiate f with respect to y, holding x and z constant. And finally, df by dz means differentiate f with respect to z, holding x and y constant. Okay, and it's the same thing when we take the higher order derivatives. All right, and if you ever have to do mixed derivatives, then you should always check that your results for these two match. Okay. All right. Onwards and upwards.